Emission Engineering presents Smartdraft, the draft device for fired heaters in oil refineries and petrochemical plants. Hello, and welcome to Emission Engineering. Today, we will present to you our latest development in furnace operation called Smartdraft. But what is Smartdraft? In short, Smartdraft is a device that avoids unnecessary alarms or shutdowns due to draft fluctuations on fired heaters and is patented by Emission Engineering. If you run fired heaters and you have trouble with this type of problem, we can provide you with a good solution. Let's see briefly how draft is normally controlled in a refinery furnace. Most draft measurements used in fired heaters are based on pressure differential measurement, meaning they measure the combustion chamber or firebox pressure against atmospheric pressure. As per API 535, the draft at the bridge wall should be operated in a range from -1 to -3 millimeters of water column. This negative pressure is measured and controls the flue gas damper, or in case the furnace is equipped with an induced draft fan, it controls the inlet vane damper of that fan, or the number of revolutions in case there is a variable frequency drive. Normally, the operator runs into difficulties with the draft if the following two conditions apply. A. The DCS and PLC has implemented alarm and interlock set points that alarms and can trip the heater. And B. If there are tough weather conditions such as heavy rain or wind. If you belong to an end user that has no alarm and interlock on the draft, you may think that you're not affected, but you are. The only difference is, the system is not prepared to trigger the alarm or trip the furnace, but this doesn't necessarily mean you should continue operating as you always did. The fact is, local weather is not easy to predict. Strong winds with steady direction and speed are more easy to handle than gusts of wind that change in direction and speed, especially in the short term. One has to distinguish two different effects during such weather conditions. A. Effects that really change the pressure inside the furnace, and B. Effects that don't change the pressure conditions inside the furnace, but only on the pressure differential transmitter itself. So let's take a look at the sketch here. If you have wind passing over the stack in parallel, it is likely that you increase the negative pressure inside the furnace, comparable to the Venturi effect in an ejector jet pump. One would be able to see the draft going up or absolute pressure going down. If the wind passes the stack on an angle, just the contrary may occur, meaning the draft goes down or the absolute pressure goes up. Small gusts of wind already can cause pressure changes by several millimeters of water column, sometimes even more than shown in Chart 1. If you operate close to the alarm or trip set point, a small gust of wind can trigger your furnace to trip. Now let's focus on the second branch of the pressure transmitter device, which is normally open to the atmosphere. Wind, or even a simple puff by the operator at that point, will cause your transmitter to respond. It's obvious that this would not change the pressure in the firebox, but it would definitely affect the transmitter signal. To supposedly survive this situation of an undesired furnace trip, some end users have been coming up with these solutions. A. Instead of a single transmitter, they use a 2 out of 3 voting arrangement, or B. They attenuate the transmitter signal either by applying electronic or software filters in the transmitter itself or in the DCS or PLC. Or C. They simply put a time delay on the alarm or trip. Or D. Any combination of A through C. Apparently, any of these measures can reduce the likelihood of alarms and trips. But an operator is firstly not in a position to distinguish if the pressure change has really occurred inside the firebox or only locally at the atmospheric connection of the pressure differential transmitter. Secondly, an artificial attenuation in the transmitter or DCS can pretend that a real change in draft is recognized much smoother by the operators than it is in reality. In Chart 2, you can see a draft signal without and with different levels of conventional attenuation. We assumed in the example an alarm value at -2 millimeters and a trip value at 0 millimeters of water column. The green line, which is the signal without any attenuation, crosses the alarm and trip value as you can see here. Applying an attenuation by electronics or software will artificially flatten the signal. The more the attenuation factor is, the less fluctuation will appear, and as a consequence, not even the alarm set point might be reached as shown in the red curve. But this is a decisive point. The operator got to know whether the transmitter tells him that there is a safety issue or not. If there is a real lack of draft, especially in furnaces with natural draft burners, this means the combustion process may run out of combustion air. Don't expect to see that necessarily first on the oxygen analyzers in the flue gas. Those react normally much slower than draft changes caused by strong gusts of wind, particularly if the oxygen analyzer is of an extractive type. Until your low oxygen alarm pops up, you may already run seconds or even minutes with too little air to the burners. This can have from little impact, like higher carbon monoxide emissions, up to big impact if burners go unstable. In a worst-case scenario, lack of air leads to explosions in the firebox. The difference in the way the draft transmitter is attenuated is A. Smartdraft attenuates by avoiding pressure peaks while cutting the dynamic portion of the pressure on the ambient connection of the transmitter, while B. Conventional attenuation via electronics or software simply flattens the sum of both components, without the possibility to eliminate a potential disturbance of the signal by a local effect on the ambient branch of the transmitter. This is the key difference why Smartdraft is superior to conventional attenuation. Let's have a look at some typical installations that we have been encountering in our daily work. In example 1, you see a pressure differential transmitter whose ambient connection is on top of the transmitter housing. As you can imagine, this is not ideal if water or moisture can come into the tubing, ending up at the transmitter membrane. This would falsify the measured pressure. Also, if this cap is accidentally tightened, gas or any condensate that would be trapped inside can cause a change in the pressure reading. In example 2, the ambient connection is on the bottom of the housing and simply open to the atmosphere, and therefore also prone to be affected by aerodynamic effects as we explained earlier. In examples 3 and 4, the ambient connection is inside the housing, and you might think that this is a good solution as it's protected against wind and rain. But keep in mind that wind passes by the entire housing. That can affect the inside of the housing, leading again to wrong pressure readings. Quite often one can see an arrangement as shown in example 5. Here the ambient connection is provided with a pigtail-shaped tubing, often used on Borden-type pressure gauges. Those pigtails have no attenuation effect at all, as we found out during our development of Smartdraft. In example 6, one can see a device that is normally used for a different purpose. They're used as silencers for solenoid valves and work with compressed air in order to avoid noise while purging. The material is normally sintered metal or some type of plastic. The disadvantage is they have undefined orifices and age over time, changing their porosity in an undefined manner. Furthermore, when exposed to fine particles, they tend to plug. After extended testing to find the ideal solution, we are proud to tell you this set of problems in respect to draft can be overcome from now on. Smartdraft is a device that you connect to the atmospheric connection of your pressure differential transmitter. The branch connected to the furnace stays as it is. Smartdraft has a labyrinth packing that filters the dynamic component, measuring almost only the static component of the pressure. Like this, a gust of wind or a puff of air from the operator will not affect the signal, which the transmitter generates and sends to the DCS or PLC. In other words, Smartdraft is a filter or attenuator that cuts pressure peaks caused by dynamic pressure, leading to smoother and safer draft control, and therefore safer operation of the entire furnace. Smartdraft is a plug-and-play device, meaning you simply connect it, and from there on, it works. It's easy to install, very inexpensive, foreseen for outdoor installation, and requires no maintenance. The return on investment is recovered already with the first undesired shutdown due to a draft issue. To summarize, Smartdraft helps avoid furnace trips, especially during rough weather conditions, by flattening the transmitter signal by the mechanics and shape of its construction, reducing the dynamic portion of the pressure. Increases the safety of your fired heater operation. Is a simple plug-and-play device, easy to install. Is very inexpensive. Has a patented design. If you're interested in buying Smartdraft for your operation, please contact us. Here are our contact details. We also have a datasheet available, which we will be glad to send you upon request. Thank you for your interest. Emission Engineering. We engineer your emissions.